We are Team 3. Our project title is Near Ground Air Quality Mapping, Assessment and Prediction. So why is it important for us to care about our air? Well, air pollution is estimated to have caused 4.2 million premature deaths in 2016, with links to increases in cancer, strokes, heart disease and respiratory diseases. This is not just an issue far from home. Manchester is the second worst city in the UK for air pollution. So how can we solve this problem? To solve the air quality issue, we must first measure, map and predict air quality. This will give local governments the data they need to tackle this issue. There are a few organisations currently involved in monitoring air pollution. The National Atmospheric Emissions Inventory in the UK compiles over 25 air quality parameters. However, this has a low area resolution, with only 228 measurement sites around the UK. Clean Cloud is a monitoring solution that includes data communication, prediction, and visualization. We have some requirements for our system. This was to have a 135-hour battery life, be a wireless system to make it easy to install, operate in a city outdoors, to be internet connected to allow for real-time assessment, mapping and prediction, and to monitor 2 pollutants. Clean Cloud was planned to have 10 sensor nodes around university buildings. These would then transmit data through the mobile phone network to a server where the data could be stored and processed. The data would then be used by machine learning algorithms to predict future concentrations. All of this data could then be displayed on a website using map overlays to help people understand and visualize the pollution in their area. We aim to have as close to real-time data as possible, however reading from the sensors would cost us battery life. We decided on a 30-minute read cycle, as this would give us a large amount of data and a long battery life. The pollutants we were to monitor are PM2.5 and carbon monoxide. PM2.5 are particles less than 2.5 microns in diameter, and the carbon monoxide is a toxic odorless gas. Both are produced from the burning of fossil fuels. These 2 pollutants are directly attributed to respiratory illnesses. We also decided to measure temperature and humidity, as we believe that these may have a correlation with air pollution. The node consists of 4 major parts: the power system, the microcontroller, the communication system, and the sensors. For the prototype, we have 3 sensors: a carbon monoxide sensor, a PM2.5 sensor, and a combined humidity and temperature sensor. For the power system, we specified a battery life of 135 hours. It was decided to use 4 lithium-ion batteries in series, as these have very high energy density and low self-discharge rate. After calculating the energy consumption, it was decided that this would provide us with the necessary energy. For the microcontroller, we decided to use the ATmega 328P. This microcontroller was chosen due to the ease of development, with an abundance of software libraries available and for its low power consumption. Finally, the communication system. For this it was decided to use the 2G network. This was chosen due to the high coverage and ease of connecting to the internet. This would allow for the nodes to be placed anywhere where there is 2G service. Once all the components were chosen, the estimated cost for a single node was £88.25, with a total cost of a 10 sensor node system coming into an estimated £882.50. Each of these subsystems was tested and proven working, however a full system was not completed. This was due to the COVID-19 pandemic. The data we gathered would be stored in an online database. This was successfully tested by sending dummy data from the GSM communication system to the SQL database. This could then be viewed easily online. Machine learning was used to predict future values of PM2.5. Ideally, we would have liked to use our own data. However, as we had no measured data ourselves, this was done using a dataset from the Zhongjin air quality site in Beijing. Multiple models were tested that included multiple linear regression and artificial neural networks. After testing, the best model was the artificial neural network, which predicted PM2.5 with 75% accuracy 2 hours into the future. To visualize and display the data, a website and app were developed. These had a map with points showing where the data was collected. These displayed values from dummy data. The points could be clicked on. This would display graphs of the data. We also generated heat maps. This required us to interpolate the data from our nodes over a 2D area. Inverse distance weighting was chosen, due to the natural look and because of its ease of adding extra nodes. There are a few places where further work could be completed on the project, mainly the production of a working prototype network. This could then be used to confirm our machine learning algorithms. Additionally, other machine learning algorithms could be implemented, such as long short-term memory and vector support machines. In conclusion, the project had many successful outcomes in machine learning, design, and data processing phases. However, unfortunately, we were unable to manufacture due to the COVID pandemic. Thank you for watching.